Now we want to continue with example 41 and really deal with the last part of the question, which says that if mass m1 is displaced by 1 millimeter, we'll take 1 millimeter as positive, it's displaced 1 millimeter downward, then determine the response of the 2 degree of freedom system in time. So if you pull this thing down 1 millimeter and you let it go, then m1 and m2 would oscillate, right? So what we want to do is we want to determine what is x1t and what is x2t. How does it vibrate? And you'll see how the natural frequencies come into play, because obviously if you give something a small displacement and you leave it alone subsequently, then it oscillates with its natural frequency. And in this case, because it's a 2 degree of freedom system, it oscillates with both its natural frequencies. So let's look at how this system is going to behave, right? Now let's go back and recall all the stuff that we derived previously. We said that what was previously done? We said previously we saw that omega 1, the first natural frequency, was equal to, get it here, 1.58 radians per second. Omega 2 was equal to 2.45 radians per second. And the mode shape for omega 1 was x1, x2, 1. It's going to be equal to, when x1 was 1, then x2 was 2 times x1. And for the second natural frequency, when you had x1, x2, if x1 was 1, then x2 was actually going to be negative 5 times x1. And that was the first and second mode shape. Now again, this is just a relative term, right? It tells us that for the first mode, if the response of m1 is a certain value, then the response of m2 is 2 times that value when it's oscillating at 1.58 radians per second. For omega 2 at 2.45 radians per second, if m1 oscillates at 1, then m2 oscillates minus 5 times what x1 oscillates at, right? So that's how you should be interpreting those mode shapes. Now, what does that mean? Well, to understand what it means a little bit more in terms of calculating the actual response, we need to just go back and recognize something. We need to recognize that when we started this derivation, for multi-degree of freedom systems in the very first lecture, we assumed that x1t and x1t had oscillations that were harmonic, which meant that they essentially oscillated like this, with a sine omega t plus phi term, right? That's what we assumed. Sometimes it's nice to use this sine omega t plus phi term just because of the significance of that phi term, of that phase term. But for multi-degree of freedom systems, when we're looking at using the initial conditions, the way we want to represent that is really with its equivalent form, which is that this sine omega t plus phi term can be represented as a constant c1 cos omega t plus c2 sine omega t. So you want to represent it in this form. So basically what I have in red here is the same as the sine omega t plus phi term. Now, how am I going to use that data? How will I use this information that I have here? Well, it's simple. The first thing is, again, it's so important that you recognize that x1, the displacement of this mass m1 as it oscillates up and down, oscillates with 2 frequencies. It oscillates with an omega 1 and an omega 2 term. So I'm going to say that in terms of it oscillating with an omega 1 term, I'm going to just change this constant C1 and C2, and I'm going to call it A. This is for mass 1, right? Just going to draw a line here to show you that it's... But x1, the displacement of mass 1 is going to be equal to A cos omega 1t plus B sine omega 1t. And this really what I have in bracket in blue here is how x1t oscillates with just the omega 1 frequency, right? Or the first mode of vibration. Then you want to say, well, I need to include the second mode of vibration, and I'm going to put that second mode of vibration in orange, right? I'm going to say that how well. It's not going to be the same as A and B. Maybe it might start with C. And it's not going to be cos omega 1. It's going to be cos omega 2t plus D sine omega 2t. Yeah? So you end up with that, and it goes mathematically. You can look at it, and what you should be seeing is that, well, listen, this thing is oscillating sinusoidally with a frequency omega 1, plus it's oscillating with a frequency of omega 2, and what I need to know is I need to start to determine what are the amplitudes it's oscillating with for omega 1, and then what are the amplitudes it's oscillating C and D for omega 2. But the system is not just oscillating with x1 alone, it's also going to be oscillating with an x2t, right? And this is where the interesting part comes into play, and where you start to recognize, you say that, okay, but wait, x2 vibrates relative to x1. That's what my mood shapes showed me. So if this is my first natural frequency, and my first mood shape showed me, which corresponds to omega 1, that when mass m1 oscillates with 1, mass m2 oscillates with twice that value. So regardless of how mass m1 oscillates, mass m2 or x2 oscillates twice as 1. So what that should tell me is that, well, if x1 oscillates at, I'm going to write it in red, if x1 oscillated with this in A cos omega 1t plus B sine omega 1t, and I just showed from the first mode shape that x2 is twice x1, then really x2 is just going to be 2 multiplied by that value. Now how am I going to do it for the second mode shape? Well, it's the same concept really. You're going to say, well, x1 for this in the second mode, or omega 2, it oscillates with C cos, this is what x1 oscillates with, omega 2t plus D sine omega 2t. And then you say, but wait, for that second mode, x2 oscillates with minus 5 times what x1 oscillates with. So then you come across here and you say, well, maybe I should get rid of this plus sign and then sort of drop in a negative sign because it's going to have a negative to it. Then I'll put in what the factor is, minus 5. So it should be easy to see if x1 oscillates with this expression for the first natural frequency omega 1, then x2 oscillates with the twice that value for the first natural frequency, and if x1 oscillates like this for the second natural frequency, then x2 oscillates with minus 5 times that value. And it's a very deep sort of equation to kind of process, because at the same time you recognize that, listen, x1 is oscillating with 2 frequencies simultaneously, and x2 is also oscillating with 2 frequencies simultaneously. So a lot of things are happening at the same time. Our goal is to solve for what A, B, C, and D are. if we solve for what A, B, C, and D are, then we can ultimately solve for how x1 and x2 are oscillating. How do we do that? How do we solve for A, B, C, and D? Well, it's an initial condition problem. So now what I need to do is I need to go find what the velocity is. I need to find out what x dot 1 is. Right? I need to find out what x dot 1 is. And I differentiate with respect to time, and all I get really is, I'll write it like this: omega 1 A sine omega 1t. When I differentiate this term, I'm going to have a negative value on the outside here. Then when I differentiate this term, I'm going to get omega 1 b cos omega 1t. And that's for the first mode. I'll put in maybe a little blue bracket again to show you that. And I'm going to put, I'll put in a plus. And then I'm going to keep the same yellow on the inside. And I'm going to say if I differentiated this, I'm going to get minus omega 2 c sine omega 2t. And if I differentiate across here, I'm going to get omega 2d cos omega 2t. And that's going to be my velocity of x of 1. Now I can do the same thing for x dot 2. You can see, well, I have a t here. And then I differentiate across here, and you should recognize you're basically going to get the same thing like this, just multiplied by 2. So it just becomes 2 bracket minus plus. Then what am I going to put before this bracket? I'm going to rush the bracket there without leaving space. What am I going to put before that bracket? It has to be negative 5, right? Should recognize that. What you'll get is just and this is what you end up with. So to solve these initial condition problems, I need x1t, x2t, x1 dot, and x2 dot t, right? And now you're going to see how we use these expressions. Because what are the initial conditions? Well, the initial conditions from the question are m1 is displaced 1 millimeter from its equilibrium position. We'll take 1 millimeter as downwards. No velocity for m1 and no displacement or velocity for m2. So how am I going to write that? Well, I can say that for the initial conditions, x1 at time t is equal to 0 is 0.001 meters. x2 at time t is equal to 0 is 0 meters. x1 dot at time t is equal to 0 is 0 meters per second because there's no velocity, and x2 dot at time t is equal to 0 is 0 meters per second. So essentially I have 4 initial conditions now, but across here from these expressions I derive for x1, x2, x dot 1, x dot 2, I have 4 unknowns as well, a, b, c, d. So I have 4 knowns and 4 unknowns. So therefore I could go ahead and solve it in terms of a set of simultaneous equations. let's start by saying x1 at time t is equal to 0. If x1 at time t is equal to 0, you substitute t is equal to 0, you must recognize the cos term is 1, the sine term is 0, the cos term is 1, and the sine term is 0. So then basically you just have a plus c, right? So, in other words, for x1 at t is equal to 0, you're going to have a plus c being equal to 0.001 meters, right? That's what you're going to have. Now, what about x2 at time t is equal to 0? You're going to see how simple it is again. You're going to say, well, at time t is equal to 0, cos is 1, so I'm going to have a, but it's 2a, and sine is 0, this disappears. Cos of 0 is 1 again, so I'm going to have 5c, and sine of 0 is 0. So basically I'm going to have 2a minus 5c. But now I'm going to have 2a minus 5c is equal to 0, right? And maybe I could just get rid of this meters here so that you could see how it's a simultaneous equation. And I can solve that simultaneous equation because it's just a and c. So I can say if I solve for a and I solve for c, what am I going to get? I get a is 0.00714, and I get c as 0.000286. So I've solved for a and c. Now let's say we wanted x10, the velocity, right? So x dot 10. What does that lead us to? Well, kind of recognize, you say, well, again, when t is equal to 0, this sine term disappears here. But you end up with omega 1b across here because this becomes 1. Sine term disappears here because sine of 0 is 0, and you end up with omega 2d across here. So I'm going to say that, well, what I end up with is just omega 1 b plus omega 2d is equal to 0, right? And then if I look at x2 dot 0, naturally it's just going to be 2 multiplied by omega 1b because this goes to 0. And it's going to be minus 5 multiplied by omega 2d because this goes to 0. So again, very simple. So it's going to be 2 omega 1b minus 5 omega 2d is equal to 0. Now the only way this expression is going to be true is that if both b and d are equal to 0, right? There can't be any values for b and for d to satisfy both these expressions. So actually, this one is relatively simple. B must be equal to 0, d must be equal to 0, right? So what does that mean? It means that you only have a value for a and you only have a value for c, right? Both b and d are equal to 0 for this expression to be true. So let's look at what are we going to say? Well, I'm going to say that I only have a value for a and I only have a value for c, right? So I have a value for a, I have a value for c. So x1t becomes, I'm going to keep this term here and I'm going to keep this term here. So how do I get that? I say, well, it's very clear to me that I'm going to write this in red. It's very clear that x1t is going to be equal to a 0.123714. I'll just leave it in meters. Obviously, it would have been easier to have it in millimeters. Cos omega 1t, and then we're going to have c plus 0.123286 cos as well, cos omega 2t. So you're going to end up with this expression here. And x2t, well, x2t becomes just as easy, because it's going to be 2 multiplied by a cos omega 1t, again this is 0, minus 5 c cos omega 2t, again this is 0. So essentially all you're going to do here is you're multiplying this first number by 2, and then you're multiplying this number by minus 5, right? So when you multiply this number by 2, what do you get? You get 0.00143 cos omega 1t minus, and you're multiplying this by 5, so what you're going to get is 0.00143 sine. Why did I put sine? Because it must be cosine, right? Omega 2t. And this is your response. Now you can go ahead now and you can actually put in values for omega 1 and omega 2. So let's change it to millimeters. Let's say, well, this is the answer in meters, just to be clear. Right? Put meters here and meters here. But let's just change it. Let's just change it to millimeters now. It'll look a little bit more appropriate. And what I'm going to do is substitute the value for omega 1, because remember we calculated omega 1 all the way on the top here as 1.58 and omega 2 as 2.45, right? 1.58, 2.45. Millimeters. And these expressions, really these expressions that I'm about to circle in orange, are your expressions for the actual displacements of x1 and x2 in time when there's the given initial conditions.